Hands-on, optimizing large datasets in Pandas. Working with big data in Pandas is powerful, but optimizing for speed and memory is key. In this lesson, we will load real-world data, explore efficient data types, use chunking to read large files, apply vectorized operations, save memory with categories, handle missing data cleverly, filter efficiently, aggregate and group smartly, merge and join big datasets, reshape and pivot quickly, use time series efficiently, visualize with Pandas built-ins, practice with a mini Titanic challenge, review best practices and speed tips, tackle troubleshooting tricks, try a hands-on challenge. Let us begin optimizing your Pandas skills. Running the cell now. First, we suppress unnecessary warning messages so that everything is clear and uncluttered. Next, we import the warnings module and set it to ignore all warnings. Import numpy as np. We set the random seed to 42 for reproducibility. Running the cell now. Here, we set up the environment by importing essential libraries and suppressing warnings to keep the output clean. Although there's no visible output, this step ensures reproducibility with a fixed random seed and prepares us for loading and optimizing large datasets without distraction. This foundational setup is crucial before diving into performance-focused data handling. This comment indicates that we are setting up the Titanic dataset for analysis. We import the Pandas library, which is essential for data manipulation. Here we specify the URL where the Titanic dataset CSV file is hosted. We read the CSV file from the URL into a Pandas data frame called df. We print the shape of the data frame to see how many rows and columns it contains. We print the first 3 rows of the data frame to get a quick look at the data. Running the cell now. Here, we've loaded the Titanic dataset, which contains 891 rows and 12 columns, giving us a manageable yet real-world-sized dataset to practice optimization on. Notice the mix of numeric and categorical columns like p-class, sex, and fair, which will be important when we optimize data types for better performance. This initial view sets the stage for exploring how Pandas handles diverse data and the potential for memory improvements. Why optimize? Big datasets can make Pandas slow or crash with memory errors. Optimizing lets you work with more data without specialized hardware. Good habits prevent frustrating errors down the line. Running the cell now. We check detailed memory usage for each column in the data frame. This helps us spot columns that use up lots of memory. Running the cell now. This output shows the structure and memory usage of the Titanic dataset, highlighting that it has 891 rows and 12 columns with various data types. Notice key columns like the name, sex, and ticket are objects, which often consume more memory, and missing values are present in age, cabin, and embarked. Understanding this helps us identify which columns might benefit most from optimization to reduce memory load and improve performance on larger datasets. Text columns often waste lots of space when stored as objects. We convert categorical text columns to the categories type. This can save memory and make some operations faster. Let us check the new D-types for these columns. Running the cell now. This output confirms that the specified columns have been successfully converted to the category data type, which reduces memory usage by storing repeated values more efficiently. Notice how these columns, originally likely strings, objects, are now categories. This optimization is key to handling larger datasets without slowing down or crashing Pandas. This step exemplifies good practices to make data processing faster and more scalable. We check the detailed memory usage again. This shows the difference after using categories in text columns. Running the cell now. This output shows the data frame structure and memory usage after optimizing certain columns to the category D type. Notice how for columns now use category, significantly reducing memory compared to storing them as object or integer types. This confirms the lesson's goal. Careful type conversion helps Pandas handle larger datasets efficiently without excessive memory use. We add a comment explaining that we will downcast numerical types to save memory. We convert the aged column to a smaller floating point type to save space. We convert the fair column to a smaller floating point type to save space. We convert the p-class column to a smaller integer type to save space. We print the data types of the age, fair, and p-class O columns to check the changes. Running the cell now. This output shows that the age and fair columns have been downcast to float 32, and the p-class to int 8, significantly reducing their memory usage. Notice the smaller data types. This is the key optimization step that allows Pandas to handle larger datasets more efficiently. The intent here is to save memory without losing meaningful precision, preventing slowdowns or crashes when working with big data. We start by noting that missing data needs to be handled carefully. Here, we print the number of missing values in each column. Next, we fill the missing values in the age column with the median age to reduce the effect of outliers. Running the cell now. This output shows the count of missing values per column before filling them, highlighting that age has 177 missing entries. The code then efficiently fills these missing age values with the median, a strategy that avoids dropping rows and reduces memory waste from nans. This step demonstrates an important optimization habit to handle missing data cleanly, enabling smoother processing on large datasets. This comment explains that the following line uses a fast filtering method called query. We create a new data frame with only rows where the age is 18 or older. We print the first few rows showing the name and age columns to verify the filtered data. Running the cell now. Here we use query to quickly filter rows where age is 18 or older, creating a smaller data frame of adults. Notice the output retains only relevant columns and shows typical adult ages, illustrating how filtering reduces data size for faster, more efficient processing. This step is crucial for optimizing workflows when handling large datasets. This line explains that vectorized operations in Pandas are preferred over explicit loops for performance. This line calculates each passenger's family size by adding the number of siblings, spouses, parents, children, plus 1 for the passenger themselves. Running the cell now. This code adds a new column's family size by vectorized addition of sib_sp and parch plus 1, efficiently creating a key feature without slow loops. Notice how this approach leverages Pandas' optimized operations for faster processing, which is crucial for working with large datasets. This method exemplifies how small, thoughtful optimizations improve performance and scalability in data preparation. Chunking loads a large file in parts, not all at once. This is essential if your memory is limited but the data is big. Here, we simulate reading in chunks of 100 rows. We show a few rows of the first chunk. Running the cell now. This output shows the first 2 rows of a Titanic dataset chunk loaded using Pandas' chunking method. Notice how the data maintains its original structure and key columns like passenger ID, survived, and fare, but is only a small subset, which helps manage memory usage. This demonstrates the lesson's point on optimizing by processing large files in manageable pieces, preventing slowdowns or crashes. Grouping and aggregation for big datasets. Pandas Group B gives quick summaries, even for millions of rows. We use it to answer questions like average fare by class or survival rate by family size. Running the cell now. Grouping passengers by class lets us quickly compare average fares. This Group B is efficient, even for larger datasets. We print the average fare for each class. Running the cell now. This output shows the average fare paid by passengers in each ticket class, calculated using a Group B ons P class followed by the mean aggregation on TAR fare. Notice how the first class passengers paid significantly higher fares compared to second and third class, highlighting how grouping quickly reveals meaningful trends in large datasets. This lesson demonstrates how simple aggregation can answer important questions efficiently even with millions of rows. Merging data frames is important when working with large, related information. Efficient joins avoid making copies and use indexes where possible. We join the dataset to itself by family size, just for demonstration. Running the cell now. This output shows the first two rows after joining the Titanic dataset with itself on the family size column, pairing passengers who share the same family size. Notice how name_A and name_B list different or the same passengers grouped by family size, demonstrating how merging on a common key helps explore relationships within groups. This step sets up deeper aggregation or comparison by family size in large datasets. Pivot tables help summarize or reorganize data fast. Here, we see survival rates by family size, a common task in EDA. Wide-to-long reshaping is efficient in Pandas. Running the cell now. This output shows the average survival rate grouped by family size, calculated using a pivot table. Notice how survival tends to increase for small family groups, sizes 2 to 4, but dips again at size 5, highlighting how grouping by a meaningful category reveals trends that inform further analysis. This demonstrates how Pandas efficiently aggregates data to summarize key metrics across categories. Use pandas.str methods to perform fast string operations on the entire column. This code splits the name column by commas and saves the first part into a new column named start. Running the cell now. Here, we've created a new column's name starts by extracting the last name from the names field using string operations. This step illustrates how pandas.str methods efficiently handle string data in large datasets, preparing it for grouping or aggregation tasks like analyzing survival rates by family last name. Notice how this transformation sets up cleaner groups for subsequent summaries. Comment describing that will set up time series data with a random sample. Import the NumPy library for numerical operations. Create a date range matching the number of rows in the data frame. Add the generated dates as a new column named FakeDate in the data frame. Set the FakeDate column as the data frame's index for time series operations. Resample that survived a column by month, compute the mean, and plot the results with a title. Running the cell now. Here, we've resampled our data by month to calculate the average survival rate over time, illustrating how grouping with time indices enables trend analysis in large datasets. Notice the line plot reflects changes in monthly survival rates, demonstrating how Pandas can aggregate and summarize data along a time dimension for deeper insights. This method is especially useful for identifying temporal patterns in big datasets. Quick visualization, value counts bar plot. Pandas can quickly plot bar charts for categorical breakdowns. We do not always need a separate library for basic graphs. Running the cell now. This quick plot compares survival rates by class. Simple visualizations help us find patterns fast. Running the cell now. This bar plot shows the average survival rate for each passenger class, highlighting clear differences in survival chances across classes. Notice how higher classes tend to have higher survival rates, demonstrating how Pandas' built-in plotting can quickly visualize important categorical trends without extra libraries. Let us apply several optimizations together. We filter for passengers over age 50 who survived. The total shows how easily we can answer real questions on big data. Running the cell now. This output shows that 22 people over the age of 50 survived. While the code here counts a specific group, the lesson focuses on quickly visualizing similar categorical breakdowns with Pandas bar plots. Counting like this helps identify key groups to highlight in those plots for clearer insights. Try to change the age cutoff and see how the count changes. Best practice tips. Always check D types to save memory. Use categories for repeated text. Downcast numbers when safe. Fill missing data up front. Use vectorized and built-in methods. Query and filter before merging or plotting. Visualize only what you need. These habits make Pandas work smoother and faster. Running the cell now. This comment warns that loading too much data at once can cause errors. We start a try block to attempt reading the file safely. Here we try to read 12 million rows from the CSV file, which is very large. If an error occurs while reading, we catch the exception here. We print out the error message to understand what went wrong. Running the cell now. This code snippet attempts to load a very large dataset, which often leads to memory errors if not handled carefully. The absence of error messages here suggests the data either loaded successfully or the error was silently avoided, highlighting why it's crucial to manage data size upfront. This reinforces the lesson's advice to downcast data types and fill missing values early to optimize memory usage when working with big files. Let us practice a fast filter. This line finds everyone under 16 in the Titanic dataset. Notice how readable and quick this approach is. Running the cell now. This output shows a filtered subset of the data containing only children under 16 years old, highlighting the name and age columns to verify the filter worked correctly. Notice the index is a date, which hints at the dataset's time-based structure, and the age values confirm the filter's intent. This step aligns with best practices by focusing data early, making subsequent type checks and memory optimizations more efficient. Pause and try this fast filter on a column in your own data. Lesson recap. Today you learned how to analyze memory use in Pandas, use the right D types for speed and space, load large files safely with chunking, leverage vectorized operations, aggregate and merge efficiently, pivot, reshape, and summarize data, handle time series smoothly, catch common errors with big data. With these skills, you can now approach much larger datasets on your own laptop. Running the cell now. Thanks for following along. If you found this lesson helpful, please like, subscribe, and leave your Pandas optimization tips or questions below. Happy analyzing. Running the cell now.